Okay, morning everybody. So welcome to MPC on FPGAs. Today's going to be quite an interactive session for pretty much most of the day. I hope you'll sort of enjoy it. So maybe some of it will seem a bit silly, but I'm sure you won't forget today. As you can see, we have a little bit of Lego ahead. So we're going to all learn how to add up with Lego in a few minutes. But before that, I'll give you guys quickly an outline of the day. Then we'll fill in a quiz. So please make sure you've got your mobile phones, your laptops, whatever open, because I think some of you probably already know a lot more than you think you do. Okay, so the outline for the day. This is me, Eric Kerrigan. I'm only going to be doing the first part of the morning. Really, most of the day we've got Bulat in charge. Is Bulat setting up, or is he in the room? There he is. So thank you very much to Bulat, who's really been preparing all the lab exercises for today, and will walk us through some of the theory, etc. and everything. And then Harsh and Deepak and Bulat and myself will go around for the rest of the day talking to you guys, right? But I will start off and I'll give you guys an intro to computer architecture. Okay. Can you all see this? Is the writing big enough in the back there? Yeah? You guys in the corner, you see okay, sort of at a slight parallel angle. Okay, and circuit design, right? So that's really what we're going to be playing around a little bit with. Okay, then Bulat will take over. So Bulat could sign off. We'll have the first lab, right? First lab. And the first lab, what we're going to be doing is we're going to implement a simple inverting and non-inverting circuit. Okay? Okay. On an FPGA. Right? So and as part of this, we're going to get a quick introduction to HDL. Okay, you're going to learn a little bit about the Z board. Okay, so that's that little beast, red beast over there in that box over there. That's where our FPGA. It's a little prototyping toolbox, and we're going to learn about Vivado, right? And Vivado is Xilinx, who manufactures FPGAs. It's their sort of design suite of software. So it's going to be a pretty easy lab, really. It's just to familiarize yourself with the environment and everything, and the board, and making sure that everything is up and running. From what I understand, some of you have installed all the software, and some of you haven't, right? So maybe that's what we'll spend for some of the time doing, is just installing. But if you want to save time, get a friend and work together on this, right? Then we'll have lab 2, right? So this one will be very quick, probably about 30 minutes or so if everything goes nice and smoothly. And we will be doing add to integer numbers. Right? Okay, so a very simple circuit. We'll take two binary numbers and we'll add them, and the little board will display what the result is. You will actually enter the number with some switches, and the board will output the result for you. Right? So again, it's just going a little bit more into HDL and exploring some of the features. Then hopefully by then, I'm hoping if all goes well, that's lunchtime. Okay. And then in the afternoon, that's when we will really start doing MPC, right? So everything in the morning is just basics on FPGA and familiarizing yourself with the thing. So in the afternoon, we will be doing an MPC controller on an FPGA, right? So that's a bit of a big leap, but Bulat has actually done most of the work for us, right? So we'll be doing this in C, right? So I think probably some of you will be a little bit rusty on the C, but hopefully it should be reasonably easy to follow what's going on, even if you're not that familiar in C, right? So some of the C to do this and actually solve it has been left out, so you will have to sort of finish some of the C code yourself to actually have the predictive controller going. And as the main thing of this, we'll be learning about HLS, right? As we sort of, there's a lot of TLAs. Who here knows what a TLA is? Anyone know what a TLA is? No one? Bulat, what's a TLA? A 3-letter acronym. TLA, 3-letter acronym. TLA, 3-letter acronym, right? So there's lots of TLAs in computing, right? So we'll learn about HLS, which is a high-level synthesis idea, right? Okay, and it's a set of software. And we'll also introduce you guys to Proto-IP, which is a set of tool chain that we've developed at Imperial for putting MATLAB and C and FPGA all together nice and neatly. In the old days, you had to do everything by hand. What we've got is just a bunch of scripts which glue everything together and automate the whole process for you, right? And the main idea behind this is what you will first be doing. You'll be doing another TLA called SIL, which stands for software in the loop. You'll do a bit of basic software in the loop testing. So your controller will just run in software. And then we will move over to PIL, right, which is processor in the loop, right? So we'll have the plant being simulated on your computer desktop, and the actual controller will be separate on the Z board, and that will be where you actually, that's your processor, right? So we're actually checking that you've got a real controller controlling a simulated plant, right? Okay, any questions on the outline of the day? Right, so by the end of the day, you should basically know something about HDL. You should be able to at least add 2 numbers in HDL, and you'll have a good framework, I think, for implementing at least a certain type of MPC algorithm and a certain type of QP solver. You'll learn a lot about Xilinx's software tools and how to use them. So it's pretty straightforward. For those of you who've never designed a computer, then hopefully you'll know something about designing a computer, right? So we need to have a bit of a change in the way we think about programming and software. And in order to do that, we need to know a little bit about computers, right? Okay. So I think that's that. So please fire up your computer. Okay, there we go. I see we've already got a few answers up there, right? Okay. I've put together a little quiz because I think you guys already know something. If you don't know what the answer is, go in there and just put a question mark, right? I sort of want to get a rough feel of who knows what it is, right? And I don't think you should be able to go on to the next question without me enabling it, right? Okay. So everybody, please just try and do this, even if it's a question mark, just so that I know you're on there, and you should be able to do that. So I think we should have about nearly 50 people coming up over there, right? Okay, no, it's okay, thanks. Okay. I think just get everybody up and running with it, and then we'll move on.
So we can only answer one question.
Yeah, you shouldn't be able to answer the next one, I think, yeah? I've got about 8 or 9 of them, right? All coming up. Okay, everyone okay? Can I wipe this off? Yeah? Okay, anyone? Shout out if I can't, right? I think, oh, I can turn around as well. Okay, very good. Whoop. Yeah, okay. Okay, any hands up if you're still trying to get on? You should be more, yeah, okay. 32. How many have we got? How many participants have we got? 50, yeah? We're still some way away from 50 here, so please do try. Just put in a question mark, anything, right? You can't connect to the internet. Use your phone. Can you connect on your phone? Yeah? Phone, yeah? Use the phone. I hope you've all got roaming or something like that, right? Okay. I think I should have 3G, yeah? I've got something in my thing. So only some of you are able to connect to the internet, right? Yeah? But some not. Okay. Okay, so right. Okay, let's have a quick look. All right. Okay, so at least most of you guys know it stands for Field Programmable Gate Array. I don't know if you were just typing this in, but maybe there is somebody who genuinely before today didn't know what FPGA stood for. It stands for Field Programmable Gate Array, as it says there. So what is an FPGA? An FPGA is a piece of silicon, right? A little chip, and it's an array, right? So a matrix, if you want to call it that, of different types of functional units, right? Some of these units, they all do different things. And you can program which units are connected, physically connected to which units, right? Okay, so that's why it's array. Gate array, because I assume it's based on, I actually don't quite know, but I assume that's from transistor gates, right? I think that's where it comes from. Unless Bulat, do you know where the gate, is Bulat gone? Yeah, where the gate comes from. But I always thought that was from transistor gates. And the word field is because it can be done out in the field, right? It's not because of electromagnetic field or anything like that, but once the processor is out in the wild, it's in an application, you can actually program it there, right? Okay. So it's not like fixed and then you can't change it, I think is the main idea, okay? Right, so that's Field Programmable Gate Array. I see a few more people have joined us. It's all flicking through, and that's very good. Okay, so that's a Field Programmable Gate Array. So another thing, right, please go ahead, type this one in. What does HDL stand for? Okay, now that you're all up online, that should be quite quick.
language?
Again, if you don't know, just put in a question mark. It's not. It's useful for me to roughly know what you guys know, but also how much you don't know as well, right? Okay, so once the number hits over 40, I'll move on, right? If you've got any questions about anything at any point in time while we wait for everyone to type in, just shout out, right? Bulat, what does the gate in field programmable gate array stand for?
One logic block of gate, something which has input and allows output, so it might be anything.
Don't quite know, okay? Well, we should probably check it out, okay. We're all guessing. Right, whoops, not that one. There we go. Right. We got a few different ones. Okay, we got high definition language, high density lipoproteins, hardware description language, right, is what it stands for, right? So HDL is hardware description language. Okay. Right, so some of you may have come across something called VHDL. That stands for Verilog HDL, okay? HDL stands for hardware description language, right? It's a language, as in like C, right, where you describe what your hardware looks like, right? In other words, what are the inputs of a certain block? What are the outputs of a certain block? The inputs of which block, the outputs of which block are connected to the inputs of another block, and then also what is the function of each block, right? So whether it adds, whether it negates something, whether it's a logic block, etc., right? So that's what HDL stands for. Verilog HDL is just Verilog's version of HDL, right? So Verilog was a company for doing it. It's the way electrical engineers design and describe electric circuits for processors, right? Yep.
Is there a difference with the very high speed? There's another acronym.
A VLSI.
There's VHDL.
Yeah.
And the V stands for another acronym, which is.
Oh, sorry. Yeah, no. There's Verilog, which is another one, right? But there is Verilog and VHDL. Sorry, yeah, I was being a bit stupid today. Yeah, okay. V stands for very large scale.
Yeah, the first letter is acronym with the starting of another.
Yeah. Sorry. Yeah, there you go. VLSI. V stands for VLSI. Yeah, is that right, Bulat? Yeah. So VLSI stands for very large scale integration, right? Okay. So there's Verilog is one type of HDL. And VHDL is another type of HDL, right? And V stands for VLSI, right? Very large scale integration, right? Or very large scale integrated circuit, however you want to do that. Okay? Now, type in, off you go. What do you guys think are the disadvantages, right? So let's have a go at that, right? So you've probably heard about FPGAs. Why have you not yet programmed with 8 FPGAs? Everything always has an advantage and a disadvantage. So the next one will be what are the advantages of an FPGA, right? But let's first focus now on the disadvantages of an FPGA. So just think of a few. If you can't think of more than one, that's fine. If you can't think of anything, just don't type anything, right? I'll give you guys, or if you want to put a question mark in, you can put a question. It'll probably form a big question mark, right? Yeah? Oh, geez. Okay, not even I know, right?
Very high speed integrated.
Oh, very high speed integrated. We have, yeah, okay. VHG, okay, yeah. This VH-SIC. Not even I do, right? Okay. The students know more. Very high speed integrated circuit hardware description language, right? Okay. So that's what VHDL stands for, right? But they're all HDLs, right? So sometimes you'll hear people chucking the word VHDL when they really don't mean necessarily that particular language, right? It's like, I don't know, C++ and C#, right? If you want to call it the differences. Is that fair to say? Yeah? Okay. So Verilog is a different one. Okay, so let's have a look. What are the disadvantages of an FPGA? Expensive, right? Okay, that probably is true. It's not as cheap as a normal processor, right? You know, so for the same computing power, you could argue, however we measure that, it is more expensive. Some people here say the power consumption, right? Okay, now that's probably true to some extent. You're paying a price, right? You know, but you're paying a price by being able to reconfigure things, right? So everything isn't optimally placed in terms of speed, in terms of energy, in terms of area usage, right? But actually, if you are very clever at programming an FPGA, you can actually make it more power efficient per operation, right? So maybe on raw footprint, you could argue it's not the most efficient. If you're not very clever about it, then it probably would be due. I would have actually have thought that one of the main disadvantages that most people think, it's this one, hard to program, right? It pretty much is, right? If you want to go straight to HDL and you're a chemical engineer, it's going to be really hard, right? You've probably never really got into grips with designing a circuit or anything like that, and so this will be a very big, strange beast to you. But if you're an electrical engineer, probably you've done some HDL, right? So can I have a quick show of hands here who has done HDL as part of their undergraduate at some point, yeah? Okay, so we have a few, right? So it's not completely. It's not user-friendly, right? You know, as we say. It's slower than an ASIC, right? So what do we mean with slower? Okay, so there are many ways we could probably interpret this. If you look at the clock frequency of an FPGA, it's usually lower, right? So I think the one that we've got there is 100 megahertz, right? It's a 100 megahertz clock. The fastest ones are of the region of, say, 200-300 megahertz, right? Or
Now they are also 500.
500. Okay, so that's about as max as you can get it, right? Whereas we know that often Intel processors are of the order of about 3 gigahertz or more, right? So if you just measure speed by clock frequency, then yeah, it's not as fast, right? But because you actually can design it on purpose, you can actually make it faster in terms of the number of operations per second, right? Fixed hardware structure, right? That is true. As I said, you know, the array where they are that's fixed, but you have the freedom over how you put that together. Okay, what else do we see that pops up there? Okay, cost. Yeah, expensive. We've got roughly the same thing. Right, so there's a whole bunch of reasons. Clock frequency is popping up. Pretty much everything seems to me to be about right. Okay, but what do we think are the advantages of an FPGA? Thank you. Okay, so let's have a look. It's fast, right? Okay, yeah, it's right. It's fast, even though it's got a very low clock frequency, right? And why is this possible? This is possible because most existing sort of Intel processors, they have a fixed architecture, and this may not necessarily be suitable for your algorithm, right? So it's a general purpose processor, so it's a master of all, jack of all trades, master of none. I don't know if you've ever heard of that expression, right? Meaning it can do a little bit of everything okay, but it's not very good at particular things, right? So what you can actually do with an FPGA is you can say, I've got a very particular algorithm. I do lots of vector-vector multiplications, and I need to speed this up as much as possible. So if you're very clever about it, you can actually, even though you're running at a lower clock frequency, you can actually do a lot more computations. And hopefully we will get a feeling of why that is the case when we start designing our own computer, okay? Prototyping, I see, is the next one, right? So FPGAs are often used for chip designers before they actually make the final chip, right? They actually test it out on an FPGA before they send it off to spend a lot of money, right? So if you're going to have a mass market chip, it's usually a good idea for prototyping. So at Imperial, we like to think of our FPGAs as the lab on a chip, right? So we are playing around with fundamental ideas in terms of algorithms and fundamental ideas in terms of computer architectures, and we're using FPGAs as a prototyping tool to demonstrate that this is potentially useful. It's parallelizable, okay? So you've got lots of computational units. You can add them up as much as you want, right? So it's small compared to a desktop. Yes, okay. But arguably, you could also just have stuck one of those FPGAs in a desktop machine as well, right? And you guys will probably know tomorrow Arduino is also a small little thing, right? It's not so much the processor, you know, it's the unit and everything that's around it. Let's see, faster time to market. That's if what you want to do as a purpose-built chip. Energy efficient, right? Again, as I say, right? Even though you are paying a price for it, if you actually producing a lot of results each clock cycle, the overhead that you're paying for that energy actually pays off in the end, and it can be 10 times more energy efficient than state-of-the-art CPUs. So I don't know how many of you are aware of this, but Microsoft, for example, is using FPGAs, are starting to put FPGAs into their data centers, right? And the main reason for this is because they do a lot of a certain type of operation, and if they code that into an FPGA, they're running much more energy efficient, right? Sometimes 10 or 100 times more operations per second per watt, right? So that's actually a measure of computing efficiency that's very trendy nowadays, right? It's how green is your computer, and in other words, how many operations can you do per joule of energy, right? What else have we got there? Yeah, you can tailor it to your algorithm. What am I not seeing there? Small numbers. I'm not quite sure what small numbers mean. I guess that's if what you want to do is you're going to be like a Formula One company, right? And you're only going to have a few chips, right? So you don't want to manufacture a super fast chip for that. That's what I'm guessing that means. That makes sense. Reliable, right? It can be reliable. People send FPGAs out into space, right? And the reason they send things out into space is because often the tracks, the size of the tracks, the silicon, the electronic tracks is quite broad, right? It's quite wide. In space, things are bombarded by cosmic radiation. And if you've got cosmic, and that will actually affect the electronic circuitry, right? So if you actually sent up the latest, greatest, very fine scale nanometer chips, it will actually produce the wrong result. So what people often do is they send up an FPGA. It has bigger tracks, right? And if anything goes wrong, you can in principle program it remotely, reprogram it remotely so that you don't use the faulty components, right? So it's reliable in that sense. Reconfigurable, right? Okay, so yeah, if you don't like what you see, you can do something else, right? Or even in runtime, in principle, it can reconfigure itself. Let me see. What I'm not seeing here easier is you can guarantee how many clock cycles a computation will take, down to the clock cycle. There's no operating system messing around with things. So if you want to give hard real-time certification of how long your computation is going to take, you know exactly, right? It's not, you know, if the algorithm is a fixed iteration algorithm, right? Obviously, if it's an if-then type thing, then you can have a bit of unpredictability, but it's a lot more predictable than having a Windows machine interrupting things, right? What else am I not seeing there? Flexible memory structure, right? That is absolutely key, right? In most processors. If you look at the new Intel processors, most of it is memory, actually, right? And memory and how and where it's located is absolutely critical, as we will see later on in Bulat's presentation. And what we've been doing a lot, which I don't quite see here either, is you can work with any number representation you want. You don't have to work with double precision floating point. You don't have to work with fixed point. You don't have to work with 32 bits. You can work with any number of bits that are necessary for you to do the computation in any number representation you want, right? And this can have big consequences because floating point can be 10 times more expensive in terms of time, in terms of area, and in terms of energy, right, than a fixed point representation. And you don't always need 64 bits to do a computation. Often you can only measure the thing to 8 bits, right? So why should you be doing your computation in 64 bits when you only measure in 8 bits, right? So a lot of the work that we've done at Imperial has to do with working with the fewest number of bits in the simplest number representation possible. Okay, what else am I not seeing? Otherwise, there you go. Okay, you guys already know a lot about why you are here today. Now, an FPGA consists of a number of units, and I want you guys to be pretty with this one. DSP, right? It consists of DSPs, BRAMs, LUTs, and FFs, right? Okay. So quickly type in, what do you think that stands for, right? Digital Signal Processor, right? So an FPGA is made out of a whole bunch of DSPs, right? These DSPs are there to save you memory. So in many algorithms, we all do a certain type of thing. So in infinite impulse response filters or finite impulse response filters, the FPGA manufacturers have essentially made mini processors, a whole bunch of them inside your processor so that you can use this, right? So you'll have DSPs in there. You also got BRAMs in there, right? So what does BRAM stand for? Block RAM, block random access memory, right? Okay, so it's random access memory. Okay, you need memory in there. Random access because you can read and write in any sort of timing order you want, and a block because there's block units of it. They can sort of, you can't have whatever arbitrary amount you want. They come in certain blocks, right? So it's block random access memory. what does LUT stand for, right? So there's some DSPs on board an FPGA, there's some block RAM, and then there are a bunch of LUTs. A lookup table, right? Okay, lookup table. The lookup table is basically there for all your combinational logic or combinatorial logic, right? Okay, so anyone who's done a digital circuits course, right? You know, you will know what I mean with a combinatorial logic. Basically, you have blocks of silicon and you can send a signal to them to be whichever logic gate you want them to be. Whether you want them to be an AND gate, an OR gate, an XOR gate, a NOT gate, any other kind of gates, XNOR, whatever, right? It depends on the manufacturer, right? So you can connect a whole bunch of these lookup tables. You can configure them as to what you want them to be and or not, and you can connect them to other lookup tables, right? So you can make all sorts of interesting things like an adder, right? A half adder, a full adder, all that kind of stuff in principle by connecting up lookup tables, right? And then FF, what does that stand for? Nobody, yep. Flip-flop, right? It's not the thing you take down to the beach, right? It's a flip-flop. It's a kind of, again, it's made out of a bunch of AND, OR, and NOT gates and some other capacitors. And that's basically the bit that gives you a bit of memory. Okay, there is a combination of memory. But if you want to implement a sequential logic circuit, you need these flip-flops, right? So you may have encountered them either in your digital circuit course, you may have encountered them as set, reset latches, right? The word latch you may, so you either set a signal high or low. You've got D-type latches, which is just output is the same as the input. But they typically are all synchronized via a clock, right? Okay. What else can you do with them? You may have heard about JK flip-flops or toggles, right? Again, these are all flip-flops, right? So they things to build up state machines, a bit of memory. So when you start adding 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you want to maybe count where you are by setting the states of these flip-flops, right? So flip-flops and LUTs, these are really the main building block, I would say. You've got a lot of those, and every time you want to have a functional unit, you'll be chowing up a few of those. Now, you can either do it at the really low level and say, I want these many LUTs connected to these many LUTs, and these flip-flops connected to these flip-flops, but that's really what an electrical engineer would be doing, right? The good news is that Xilinx has actually provided a lot of libraries which do this for you. So you can say, I want to add up some signals, and it will configure a bunch of LUTs and flip-flops for you. So when you actually run your software, it'll tell you how many LUTs and flip-flops you've used, right? So that's how much silicon you've basically used. It'll also try to be clever and maybe use a few DSPs there as well, right? Depending on your operations. And the BRAM is really your main source of memory, but you can often configure flip-flops as memory as well. So as registers, right? If you've done a course in computing. Okay, so these are the main building blocks of FPGAs. Any questions there? And then you've got, again, just what we call a routing matrix, right? A routing matrix, right? That's just the circuitry around everything where you can connect units to other units, right? Okay. And where these things are, where the flip-flops, LUTs, BRAMs, DSP, and how many there are, these depend from processor to processor. Okay, so I think that's the end of our quiz, right? I wonder if we want to just take a 5-minute break before we continue. Yeah, just to stretch, rotate, I don't know, shout out. A little bit about computer architecture. All right, so a computer, in order to build a computer, you're going to need three things, right? You're going to need processors, right? And what do I mean with a processor? I mean, you can think of it in any kind of level. You can think of it as a basic low level, just 2 or 3 transistors, which are doing an AND, an or a NOT operation. Or you can go think of it at a much higher level, like an actual computer, or you can think of the processors as a rack of computers, or you can even think of a processor as a big data farm, right? You can think of it at different levels of abstraction. You're going to need a processor. You're going to need a communication subsystem, okay? Processors need to talk to each other, right? And more importantly, I probably should have added this one first, you need memory, right? The data needs to be stored somewhere, and this data needs to be moved to a processor, amongst the processors, and then back into memory, right? So communication system, this can be anything. Again, you can think of it as either an actual piece of silicon wire on an actual processor, right? So there's a small little bit between transistors. You can think of that as the communication subsystem. You can think of it as between processors. You can have a piece of wire. You can have wired Ethernet, right? You can have wireless. All of these things as communication subsystem, right? And again, you can be thinking of communicating between computers, whole desktop computers. You can think about communicating between data farms, right? Whichever is the appropriate level of abstraction. Memory, when we mean memory, we again mean all the way down to an actual transistor, actual capacitor, which is storing a charge, right? To RAM chips, right? That you can buy, like the 8 gigabyte RAM or whatever it is that you've got in your computer, to hard drives, solid state. Tape drives are not dead. Tape drives are still pretty much the cheapest way to store data, and it's used in data farms, right? It's maybe slow access time, but they actually do store things on tape, right? And IBM is still doing a lot of interesting work in tapes. So memory is just anything which stores information. Now, each of these, if you don't have those three things, and you're not thinking of those three things at the same time, you don't have a computer system, right? You can't build a computer system with only 2 out of those 3 things, right? And there's a whole bunch of different architectures, but we're not going to talk about that. And when we do the design, you need to actually realize that these 3 subsystems actually consume physical resources, right? The most obvious physical resource that some of them consume is time, right? It takes a certain amount of time to do a computation. It takes time to move things from A to B, right? Okay? It takes time. It doesn't just happen instantaneously. And likewise, going to memory and getting something from memory takes time as well, right? And I think often we just think, oh, it's just the processor that consumes the time. But in different applications, different algorithms, you'll either have the communication or the memory being the thing which consumes most of the time, right? The other thing that it consumes, which we've already probably encountered, which is becoming more and more important, is energy, right? So it actually takes energy to do some work. Every time a transistor switches state, it gives off heat, right? So data farms are built next to power centers, power stations, and that is because they consume megawatts of energy, right? And in embedded applications, you don't want to be using more than a few joules over its lifetime potentially, right? So you really want to be very energy efficient on that. Communication, again, right? The minute you switch from 2G to 3G or from 3G to 4G, you'll suddenly notice your battery drops, right? Again, the faster you do things, the further away I might be from my station, the louder I need to shout, the more energy I'm going to be using, right? So you need to think about that. Memory consumes energy as well. You often need to constantly recharge RAM, right? So if you don't do that, it'll just, the state will disappear. But again, if you want to store something on a hard drive, you need to use energy to switch that. So you want to think about that. Right, okay. And then the other thing which it consumes is space, right? A processor actually consumes a certain amount of silicon, right? And actually the cost of a processor lies anywhere between a quadratic function to the power 4 of the area, right? So if I make a processor which is twice as big, it's going to cost me at least 4 times, right? Okay, that's just the way of the process, the way it goes on. So again, if I want a very big supercomputer, a data center is as big as a football field, right? Okay, so you have to think about how much space you're going to be consuming there. And the space is sort of related to the energy as well, right? Communication consumes space, right? If you look at an aeroplane, there's a lot of cabling, right, happening because of communication between different subsystems, right? Fly-by-wire, right? It actually consumes a serious amount of cabling. Wireless also consumes space. It consumes space in 2 ways. In the electromagnetic spectrum, right? So if I use up a certain bandwidth, that's there. It's not for someone else to use, right? And likewise, if I build an antenna has a physical size, right? I can have an antenna this big or this big. Depending on how big it is, I'll be able to transmit different amounts of distance, right? And memory as well, lots of memory, very big, very little memory, very small, right? So when you actually design a computer, there is no such thing as a single efficient design, right? You're going to have to trade off time against energy against space, right? So what do I mean with that? So let's say, for example, I've got the time it takes for a computation, and I've got the space for the computation, right? You may be able to produce a sort of Pareto optimal curve like this, right? Or an efficiency frontier or whatever you mean, right? So any design down here might be impossible, right? So it may be impossible to achieve a very fast computer using very little energy, right? Okay, so I can either have a supercomputer, you know, the size of a football field over there, that's very fast, or I can have a slow computer that actually fits inside a person, right? If I want to say do anesthetic control, right? So you have to do this kind of trade-off. And so when we actually mean, when you speak to most circuit designers and they say, oh, your design is not efficient, what they mean is it's not somewhere on that curve, right? And you have to think about the application as to where you can be on that. So you can't achieve the impossible necessarily, but this is a dumb design. That's a good design. So you could argue that for many applications, if you chose an Intel CPU, you'd be choosing one of these. And the idea is that hopefully with an FPGA, you get closer to this, right? So this is maybe what you could achieve with an FPGA, and this is maybe what you could achieve with an ASIC, right? An ASIC is an application-specific integrated circuit, right? So we actually design a circuit, mass produce it on a big fabrication plant, right? So this is maybe for your algorithm, the CPU would be up there, and we hope that for your application you can do that with an FPGA. Okay, so you have to do some trade-offs. Right, okay, so now let's design our own computer, right? Okay, we're going to be looking at these 3 subsystems when we design our own computer, and we're going to be probably looking, we should be able to look at most of these, right? I'm not so sure how much we will get a feeling of this, but I hope we're going to get a feeling of at least the time and the space, right? So this is where we become interactive, right? We're going to be doing this, and I'm going to need some audience participation from pretty much everyone, right? Okay, so let's have a look, see how we do this. Is it okay for me to wipe this off? Yep, okay. Okay, so what are we going to be doing? We're going to add a set of numbers. Adding a set of numbers. Right? Okay, how do we add numbers? Here's my numbers, right? So if I take one Lego block and I add it to another Lego block, I've added two numbers, right? If I then go take another number, another block, and I add it, and I've done that, right? So that's how I add numbers, right? Okay, let's do that. Right, I need a volunteer, particularly the biggest one in the class. Niels, right? Okay, where do you want to sit? Somewhere. You can probably sit where you are for now, okay? And I need the fastest. The other one, I need the fastest, well, sprinter. It's usually somebody small and lean and can move quickly. Who's that? Anyone? You want to go? Anyone? Okay, good. You want to come over here? You're going to be our communicator, right? So we're going to have memory, right? We're going to have memory. Oh, let me do that. Right, memory. Over there, we're going to have a communication channel, and then we're going to have our adder over there, right? And that's Niels. And Niels, you're big, right? Because you're consuming a lot of lookup tables, right? You're a bunch of lookup tables all configured up to, in one clock cycle, add up some numbers, right? And you're our communication channel, and I've got, this is memory, right, over here. And you need to take one, you can only carry one at a time, right? To Niels. Niels, you can hold on to a number, right? You can take another number, but you can never have more than two things, right? Okay. And when you get one, add them, right? Okay. So I need a timekeeper as well. Do we have anybody with a stopwatch or something like that? Harsh, yeah, you got a stopwatch, right? Okay, so yeah, I'll just write it up once we do it there, right? I'll count the number of numbers, right? So let's add up 4 numbers. Yeah. Okay. Are you? Wait. Hang on. Harsh.
Start.
Right. Are you okay?
Yeah.
And off you go. You can't give him more than. You know, you have to wait, right, until he's actually done one day, right?
Okay.
Yeah. No, it's all right. Yep. You can come back and forth in the meantime. And you need to bring the number back.
18 seconds.
18 seconds, right? Okay. 18 seconds, right? To add up 4 numbers.
But doesn't the communication need to, if you put 2 numbers together, the communication should bring it back to the memory and back to him again, and another one?
Okay, so memory can only store one number. This is a number, right? This is a number. This is 2 numbers, right? The communication channel can only carry one number. If I want the communication person to carry 2 numbers, I need 2 people, right? Okay, so I've just got 1 here, right? So I've got 18 seconds, 4 numbers. To prove it to me, I need another sprinter. Can we have another sprinter to take 2 numbers, right? You want to come with us? Okay, so 18 seconds, 4 numbers, 1 communication, right? So I'm going to say 1 communicator plus 1 adder is 18 seconds for 4 numbers, right? Okay. Now, there are rules here, right? You can't carry more than 1 number. You can't hand him a number if he hasn't added up, right? So if he's still busy, you have to wait before you hand over, right? And if both of you come there at the same time, you can't both give him a number. He can only take 1 number from you, right? Okay?
So we both run.
Okay, so are you ready here? So let's do 4 of these, right? Are you ready, Harsh?
Yes.
Okay, so these 4 numbers, right?
We both run.
Okay, are you ready? Go. Okay.
11 seconds.
11 seconds, right? So 11 seconds. So it's not 9 seconds, right? So it's now 11 seconds with 2 communicators, right? You're seeing that by me adding more communicators, I speed some things up, but not really, because it's to the end of the day, it's limited to how fast Niels can do things, right? Okay. So 1 communicator, 1 adder gives us 4 numbers, 18 seconds, 11 seconds. Okay, so now let me see, how many numbers have we got, right? Okay, we're going to have quite a lot of numbers here. Okay, so I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right, okay. Right. Okay, so I need, shall we say, yeah. Okay, so let's have a good workout here. Let's have 2 more communicators. And 2 of you guys come up. All right. Okay. Okay. First of all, let's just do this quickly, right? We're getting a good hang of this, right? So now I'm doubling my communicator, right? So okay. So I've got 4 communicators, 1 adder. Are you ready, Harsh?
Yes.
Yeah. Off you go. Okay, hang on. Yep. Say when you're ready. When you are, Harsh. Yeah.
Okay, start.
Oh, sorry, just 4. Right. Yeah. Sorry. Yeah. Okay. Yeah, that's 5. Yeah. Okay. Let's do that again. Yeah. We just want to keep it at 4 numbers. Yeah. Sorry. 4 communicators, 4 numbers. Right. Okay, so ready, Harsh, when you are?
Start.
Okay, and you got to get it back. Harsh?
10 seconds.
10 seconds. Not a lot better, right? So how are we going to do this, right? Any ideas as to how we're going to go faster? Any suggestions? We have another adder, right? We want more Nielses, right? So we got a Niels there. Any more Nielses? You're Niels? Niels? Another one there, and maybe one over there, right? Okay. So we got 4 adders over there. Okay. I want you to add up 16 numbers, right? We're going to add up 16 numbers, right? So now, what do you guys think? What do you want to do?
Can they pass the blocks with them?
So, but how are you going to do this, right? So we got memory. We got one memory over here, right? Right. And then we're going to have 1 adder, 1 adder, 1 adder, and 1 adder, right? Okay. So what are we going to do? Who wants to do and pass to who?
Well, first we add 4, and then
4 each one, and then
I
we
will
sum
add.
up.
Then he gives to me. I add 2. He gives to him, and then we give to each other, and then we give back.
Okay. So you're going to take 4 numbers, right? Each communicator, you say, takes 4 numbers that way, right?
Yeah.
Then 4 that way, right? And then 4 that way, and then 4 that way, right? Okay. And then you guys are going to talk to each other, right? You're going to talk to each other like that. And then you guys are going to share. You're going to do that. And then what?
And then the last 2, like the.
Okay. But you have to sit where you are, right? So we need Mr. Yeah. You guys can't, right? You got to still communicate, right? Do you think you can talk to each other? You can reach over, right? You want to do that? Okay. So those 2 are going to talk together, and then we get memory to come and bring it back, right? Okay, so 16 numbers. Right, so let's have a look. We had 4 communicators with 4 numbers, right? So if we didn't change the number of adders, right, how long do you think this would have taken? 4 times 4, right? So it's 40 seconds, right? Okay, so that's we want to beat 40 seconds, right? Yeah, that's how long it would have taken if we just had Niels, right? But now Niels has a bunch of friends, right? Are you guys ready, right? You're clear as to who's going to communicate with who. You're only allowed to take a single block at a time. Okay? Harsh, when they are and you are?
And this one.
20 seconds.
20 seconds. Woo! Okay. Okay. Now, one thing, one thing, of course, notice that we took twice as long, right? Even though we've got 4 times as many adders, right? It's not like it's a constant, right? There's a certain overhead there in passing amongst each other, right? There's a bit of memory overhead there, right? And that's going to put a fundamental limit as to how far. Are you guys a little bit, right? Okay, you expended a little bit of energy, right? You know, running back and forth, right? Okay, very good. Do we want more communicators? Give these guys a bit of a break before we move on to the next exercise. Anyone else want to replace them? I'm going to need 4 more. 4 more communicators. Another one. You guys. Another one. Yep, you go. Okay. Now we want to add up 16 numbers, right? Have I got 8 communicators, right? Yeah, I've got 8 communicators. Okay. Right, I'm going to now need more adders as well, right? I'm going to want to add 16 numbers and I'm going to want more adders, right? So what I'm going to want is I'm going to want you 4 guys as adders, right? I want 4 adders over here as well, right? So I don't know how you guys want to arrange that, right? Because remember, Mr. Communicator is going to come into you over there and has to give you some data, right?
Can we use Wi-Fi?
Yeah, Wi-Fi. Yeah, if you want to, right? That's what you would call a dropped packet, right? You know, so that's where you would get dropped packets. We can try that one later on if you really want, right? So we got 4 adders over there. We got 4 adders over there. Then I want 4 more adders. Right? 4, 8, yeah. I want 4 more adders in the middle here, right? You guys are adders, right? Okay. Yeah, there's a little square of adders over there, right? And then I want 2 more adders. 2 more adders. Right? 2 more adders. Now, okay, you've already been assigned, yeah? You guys got 4 adders. We've got 4 adders over there. I want 2 adders together behind you guys over there, right? Stick up your arms, yeah? No, right behind, yeah, the 2 of you next to each other, right? You 2 are adders, right? And then I want 1 final adder just behind you, right? You're 1 final adder over there. What we've got is we've got an adder tree, okay? So what we're going to be doing, right, is we're going to want to add 16 numbers, right? So each of you guys in the front will only receive 2 numbers, right? Then you need to get your number, not to the guy next to you, right? And the reason for this will become clear, but you guys need to get it to the middle 4, right? Okay. Sorry, I'm going from 8. Yeah, I'm going from 8 to 4, right? So each of you 4 needs to receive a number. Rely on your communicator team, right, to help you guys do this, right? Okay, so you guys.
We need also to transfer between the memories.
Yeah. So I mean, part of this exercise is that you guys need to figure out which blocks are going to talk to which blocks, right? And who's going to be the communicator for that block, right? Because that's how you design a circuit. You say, I've got so many blocks, and these blocks are going to talk to these blocks, right? The outputs of this block is the input of this block, right? So make it clear to yourself and your communicator what you need to do, right? Okay, then we've got those 4 over there. You guys are going to take results and you're going to pass so each of you, in order for you to work, you need to have 2 numbers, right? You're going to have, each of you are going to have a block of 2, right? And each of you guys, and there, you're going to need 2 blocks of 4, right? And then, oh, then I think you're done, right? Then our friend at the back, he just holds it. We'll let you out, right? You know, we'll let a communicator run all the way to the front from there, right?
Could they stand up?
So if you want to stand up, right? So is it reasonably clear, right? And go and talk to your friends. Figure out who you're going to be talking to. Make sure that. So the first 4 is the front 8. There's a front 8, right? There's a front 8, which is this 4 and that 4, right? Then we've got the middle 4, which is behind that, and then we've got a back 2.
But do we need a communicator between memory blocks?
You need to get your data from here to each of those blocks, right? And then when they are done, you take that block and you move it to the middle block, right? So some of you are going to become redundant, right?
So before was wrong, right? Because they were communicating between each other.
Yeah. So now they're not allowed. That was wrong. But, yeah, I mean, they could reach behind them, right? But we don't want to. We're going to come back to communicating with each other soon, yeah.
So that's 4, like 1, 2, 3, 4, for example. And then we
Yeah.
That actually communication is really.
It's going to be bottleneck.
Yes.
this 4, but you will be faster
Yep.
So basically,
You're the front. If you guys can just form the front row, right?
communicators have to bring it to the middle.
1, 2, 3, 4, 5, 6, 7, 8. Okay, I'll. So the communicators will come and give you the data and take the data from you, right? Okay, you don't need to do anything, right? And then the communicators will move it there, right? So we've got a rack of 8, then we've got a rack of 4, right? And then we're going to have a rack of 2, right? Okay, all right, so we may need, I'm doing, okay, so we're going to have 2, 2, 2, 2, 2, 2, 2, 2 numbers going that way, and then again, you know, we'll have things going out that way, right? 8, 8, he's got to put them together, right, okay. So that's going to give us a 4 and a 4, an 8 and an 8, and 6. Oh, they're going to get a bunch of 1s, right? Yeah, they're going to get 1. They're going to get a 1 and a 1, a 1 and a 1, and then they're going to have a 2 and a 2, 2 and a 2, 4 and a 4. Okay, everybody clear? Right? Okay. Okay, so at the moment, really what happens in a circuit is there's a clock, which does this, right? Okay. So we're going to have an asynchronous computer here, right? And we'll sort of see what the pitfalls of an asynchronous computer will be, right? Okay, so we had 16 numbers in 20 seconds. Right, so now we have more adders, right? Okay, admittedly, we'll come back to why I don't think we're going to achieve this number, right? Okay. Right, are you guys ready? Harsh?
There is one piece.
Yeah, but there is some details here about
Okay.
36 seconds.
What is that?
36.
36. So it's worse, right? You know, even than this. Okay, and why was that? Because we had a communication bottleneck over here, right? Okay, so there was a certain bandwidth and we just couldn't get all the data in here, right? So you need to think about that, right? When you design and place and do your communication network. Now, stand up, all right? We're going to do little refinements of each idea, right? So keep standing up. Now we're going to really think cleverly about our communication, right? And you guys should be, please hand it over to yourselves, to the people behind, right? Okay, so form a rack, you know, let's form this tree, right, if you guys can, right? So we want to have 8 people, then 4 people in a row, then 2 people in a row, right? That will be the best way of doing it. So each pair identify the adder that you're going to be passing it to, right? Right? Right. So here we had what, 8 communicators plus 8 adders, and we used the bus, right? We used the bus with 8 communicators. So this is what we call the bus, right? Okay, that little path down there, and the bus got a little bit blocked. Right. Everyone identified your input, where you're going to get the input from. You've identified your output, etc. and everything, right? Okay. You are not allowed to have more than 2 blocks at a time, right? Okay. So make sure everything's fine.
And they pass backwards and they can pass to the front as well?
I think one of you guys just go to the back, yeah? Okay, so 8 of you guys, give them the 2 pieces of data.
There's only one guy who will come through this.
Only one, yeah. Yeah.
So now you are
Maybe we can try one, you give them 2 pieces, like better.
Okay? Are you guys ready? Everyone clear? Harsh, you ready?
Yes, I'm ready.
Off you go.
Start.
Give him a like.
There he was.
27 seconds. Okay, it's a little bit better, but not brilliant. Okay, so I think hopefully there is a bit of a communications bottleneck here, right? But you can guys certainly see that part of what's really slowing you guys down is the fact that these guys can only carry 1 number at a time, right? If I had 16, right, over here, it'll be even faster, right? But let's keep the eight of you guys over here. We keep everything there, right? Now we've got 16 numbers, right? So now I want to be adding 16 times 4. 64 numbers. Okay, I'm going to be adding 64 numbers, right? So how long do you think it will take for you guys? 27 times 4, right? 8, 2, 8. Will it take you guys 108 seconds to do that? Less. Why?
Because we can store them.
All things being equal, that's what it's going to be, right? Let's say that's what it's going to be, right? But what we're going to be introducing now is the notion of pipelining. Okay, so what we were doing was we were waiting till the end, and then we bring the number, right? Then if we then started with the next number, then it would be that, right? Okay. So I'm going to have 16 groups of 60. Okay. So what I want from you guys is to, let me see, you want, each of you, you've got to do 4 numbers. Yeah. Okay.
2 numbers and we already passed it on the next.
Yeah. So once you've got it, you can pass on to the back, and you're ready, right? You can start with the next one, right? You know, we're going to put you, while that one is still busy computing, you guys are free to do some computing, right? So we're going to give you a next set of numbers, right? And we're going to do that 4 times. Yeah? Okay, so each of you should really be carrying 8 numbers in total, right? 8 numbers in total. So yeah, I think if you also want to maybe, we don't really, we have got a lot more of the smaller ones, right? Okay. So I'm hoping for us to beat this 108 seconds with that, right? So you guys are going to need to be particularly efficient, I think, in terms of moving things, right? And we're going to, let's make things also easier. We have another communicator which is going to take the data from the back and move it forwards, right? Okay, and as a matter of fact, I'm going to be helping us. I'm going to have 4 communicators from the back, right? So each number that you produce out, okay, so there's different ways we can think of it. We can either think of it as 4 sets of 16 numbers, or just you produce a very long one, right? So it's up to you, right? Whether you just want to produce a very long one, or if you just want to produce 4 sets of numbers, right? So what do you want to do? A very long one, right? So we just need one Yeah. Okay, good. Okay, because I think ideally we would have probably have had you guys over here. Yeah? Push everything in. Yeah. Right. So this is what we would call, roughly speaking, coarse grain pipelining, right? It's at quite a high level, which we're going to be pipelining you guys at the addition unit, right? I mean, we'll introduce another finer type of pipelining. So we know about parallelism. Okay, so the other thing, of course, that you will probably encounter is the time it took for all of this, for one computation to finish. That's called the latency, right? Okay, so that's the latency. Think of the, so the latency, sometimes people would call it, this is the computational delay, right? But in computing, we like to use the word latency. It's the time it takes between you starting the computation and you getting the result out, right? Okay. So the latency for our computation is 27 seconds, right? That's the latency. Okay. So if I just did the full computation and I then waited before I filled that again, then the latency would be 4 times, right? That for the whole addition, right? But what we're going to be doing now is we're going to use pipelining, which is the same idea as in manufacturing. You know, you each do your bit, you pass it over to the next one as you free. You don't wait for anything, right? So that's called pipelining. And the idea behind pipelining is what it does is it increases our throughput, right? So the throughput is the number of computations that you do per second, right? Okay, so once all the computations are sort of done, right? That's one way of defining throughput. Okay, so everybody ready, right? So our target is to beat 108 seconds. Everyone clear on who's going to communicate, where, etc. and everything? Each of you guys, you clear as to how many blocks you need to get? 888. Right, 888. Okay, and Harsh?
Yes, I'm ready. Let's go. Start.
One of the blocks that was super fast.
This is still winning.
That's almost over. One more.
One more in 5 minutes. You forgot. One more here. One more there. Just feel.
It's okay. It's okay. It's okay. It's okay. 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 Done. Let's say done. Yeah.
125 seconds.
So 65 seconds, right? Okay, 65 seconds. Okay. Right, okay, so clearly some computational errors along the way, right? Yeah, okay. And computers do this all the time, right? If things are too fast, you know, and you're not waiting for things, there's not a clock beating us all and making sure that we're all in time and synchronized, then you get these kind of problems happening, right? Which is why we often have a clock to synchronize things, right? Okay, so that was parallelism. So we've speeded things up, right? But not by that much, right? Okay, so we very much, it's a function of a communication, right? You know, it doesn't matter how many we now add, right? At the end of the day, it's going to be about these guys, right? It doesn't matter how many adders we've got. They're going to be, and they've done a lot of running around, right? They're a lot more tired now. You guys were relatively efficient, right? Actually, so it's actually the communication which is often taking up a lot of the. It's expensive to move data, right? By you guys just moving data very quickly to where it's needed, rather than via the bus, you saved a lot of time, right? But not as much as you think. Right? Okay, so I think that is the lesson learned, right? So maybe you guys want to sit down, and most of the comms people, I still want to form a pipeline over here, and I want to show you guys, I still need some communicators. Who hasn't communicated yet? Do we have any communicators at the back who want to come forwards to be communicators? Okay, so what I want, okay, I think this is enough probably, yeah, probably, I just need two communicators, yeah, yeah.
More like a wave.
Maybe I should let's break up the fours, right? Okay, let's use some fours. They're the ones that are the most, yep. Okay. Okay, so let me just check, right? So we got you. You're gonna go 1, 2, 3, 4, 5, 6, 7. Right, okay, good. Okay, good. Right, so you can make things faster, as you see, by using more space, but by doubling the amount of adders, you don't halve the time. Right? Okay, you do need to think about the communication structure and where the data and storage is, right? So this is why really parallelizing things is not as easy as you need to think. But the whole point is that I want you guys to think of as a computation is it's how you connect up additional units to other addition units, right? And how long the addition unit will take, how long the communicators will take, because there's no point in having too many communicators when the bottleneck is the adder, and likewise, you know, if there's only a certain amount of data that can be passed down, there's no point in trying to send more data. You'll just get a backlog, right? Right, so what we're going to be doing now is we're going to be looking at often the way which we do things in the FPGAs is really at the fine low level. So Niels here was a massive big lookup table. You were all big lookup tables. You could all do the whole addition in one single go, in one single clock cycle, right? And that's actually, if you look at fixed point addition in an FPGA, you can do it in one clock cycle, right? But what we often do is we introduce a bit of latency to allow us to have a kind of degree of parallelism without using excessive resources, right? So what we're going to be doing is we're going to turn each of you into a flip-flop, okay? So the flip-flop is just going to take two numbers, and it's only going to add one bit at a time, right? So it's going to do that. So that's what you will be doing. Then you will pass it on to him, and you will just move it by one, right? And you will just move it by one. So that's in the same way that, you know, when I'm taking numbers, right, and I'm going 1 0 1 1 1 1 0 1 1 1 1 0 1 0, roughly speaking, I will go 1 plus 1 is 0 1, 1 plus this is 1, 1 plus 1 is 0 1, 1 plus 1 is 0 Oh, sorry, this should have been 1, 1, right? 0, 1. 1 plus 1 plus 1 plus 1 is 1. 1 plus 1 is 0, 1. 1, 1 plus 1. Ah, yeah, you're right, yeah. Okay, so, okay, 1 plus 1, it's 1, 1. The 1 plus 0, 1 is 0. 1. 1 plus 1 is 1, 1, right? Okay, so this is what we're doing. Each time I'm carrying over, passing over to the next one, right? So it's a small little bit of circuitry. You can't do a lot. So let's time it. Harsh, how long is it going to take this sequential logic circuit made out of a bunch of flip-flops to add? This is not exactly how you do it, right? But this is just sort of demonstrating the idea to add these two numbers. So when you get a number and it's like this, just keep moving it. Yeah, just 1. We just want to go all the way to the end. We consider it that once you're at the end, you're done, right? Okay. So we'll have one memory guy at the end, one memory guy at the beginning, right? So two numbers there. Oh, okay. Yeah, we want to keep it like that, right? Ready, Harsh?
So I need to give one at a time, right?
One at a time, yeah.
Start.
How much? 26. Yeah, 26 seconds. Okay, so let's delete all of this, right? Okay, so that was clearly slower than just giving it to Big Niels to add in one chunk, right? So that was 26 seconds for 2 numbers, right? Okay. Right, so what we're going to be doing now is we're going to run all the way through like that, right? And then when you're at the end, you're going to come back. We're going to have a memory person taking us all the way through to here and feeding the result back in there, right? Okay. And what you will be doing is as soon as, what's his name? Robin is free, right? You will go and you'll give him another one, right? Okay, so as soon as he's free, you will do this and we'll build a chain and we'll keep doing this until we've run out of numbers here. And they're all sort of weirdly stacked up, right? Okay, we'll sort of figure out. If things break, that's all right. Yeah, okay, we'll do that. So let's see how many numbers we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Okay. Let's see how well that works, right? So 16 numbers, right, should take us times 8, right? That's 48, right? That's 16, it's 208 seconds. Let's see if we can beat 208 seconds, right? That's our goal. 2 times 8, yeah, roughly. Is that right? I mean, if my head's not wrong. Okay. Okay, are you ready? Okay, so as soon as you're done, whatever result you've got, bring it over there. Yeah. Okay. Right.
Only the top one?
Yeah, just shifted by 1, right? So you do something, right? Okay, notice there's a lot of work not being done now, right? Okay. Just pass, right? I think we're getting a bit big now, yeah? Yeah. How are we doing? I hope we're getting it there. Is it? No? Okay.
Okay, so it's 2 minutes, 12 seconds. So
120? 132 seconds, right? Okay. So with the same circuitry, right, you can actually, rather than going 208 seconds, you can go 132 seconds, right? You know, by actually, as you're waiting, doing that. Now, you could clearly appreciate that if we had minutes, you would all be doing numbers all the time. It was really only towards the end there that some of you weren't doing any work, and at the beginning, right? So it depends, and this is what's important. If you're only adding a few numbers, you don't want to have that long chain, right? It might have been better for just the 4 of you guys to have done that, right? Okay. So this is pipelining at the fine scale, right? So when you actually look at what we will be doing, Bulat, unless I'm wrong, we're going to be doing this kind of pipelining today, right? We add latency into the adders, and the pipelining will yeah, okay. So both the low level or fine grain or the big high level parallelism, we can do that, right? So you can add latency. So it took 26 seconds, right? You know, to do that, rather than, what was the original one? 20 seconds, I think. Or how long did it take you for that first edition, very first one? 20 seconds, right? So it took a little bit longer. It seems a bit, yeah, you were really slow the first time round, I think, yeah? Okay, but I guess we were learning, right? So for a little bit of extra time, right, it may not be as good as for adding 2 numbers, but it's a lot better for adding 16 numbers, right? So you use a bit more time, but that's fine. And actually the amount of silicon you'll be using will be just I know it looks like 8 Nielses, or rather, shall I say, it's more like 7 Nielses. So we want 1, 2, 3, 7. So more like 6 Nielses, because Niels is quite a big guy, right? But you will be using slightly less than 6 Nielses with the flip-flops in terms of flip-flop silicon area in terms of lookup tables, right? So you have this choice either explicitly or the compiler will work it out for you, right? So you have this knob to add latency to your adders. So this gives you more pipeline depth, right? Is what we got over there by doing this. Okay, thank you very much. Okay, so I think that's that. Right, okay, so you now know how to add up a bunch of numbers. You know about pipelining, you know about parallelism. You know that you've got adding units you need to worry about. You've got memory you need to worry about. I had this over here was a shared central memory, right? You can have a whole hierarchy memory. We could have had people carrying this blocks to somewhere else in the middle, and we could have had lots of people over there maybe running around and just a few people carrying bits through, and that's like cache, right? You guys may have heard about cache in memory, level 1 cache, level 2 cache, level 3 cache. You'll have a memory out here which is very slow to access, and maybe certain layers of memory with more faster communication between that lower level memory and the others, right? So it depends. You can design your memory hierarchy. So this was just a centralized shared memory. You could have had a distributed memory, right? Which is where you put the data where it's going to be needed, right? So I think Bulat will show us a little bit more about that. So that's again one of the key features about an FPGA is you can trade these things off, right? But there's no magic. No single Niels will beat them all, right? You know, There's time, energy, and space that you need to worry about, right? Any questions from you guys about this? This is as deep as I think we need to go, right, for circuit design. But the idea of what you need to do is what we've done physically, you need to sketch out yourself on a piece of paper when you think about computations. Think of things in terms of space, in terms of time, and movement between these things. Don't just think of computations as lines on a code. I do this, then I do this, then I do this. It's really who does what, where, and when. Right? If you do this, this is a big change in the way you think about computing, but that is the key shift in terms of really being able to use modern computer architectures efficiently. Right? Okay, I think that's that.